तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today we will look at arithmetic circuits. Computers, of course, are the most important digital systems. At least it's the most visible digital system. Whenever you say digital, immediately comes to your mind is computer. And computer consists of all these arithmetic units. Of course, there's a lot of control also. Arithmetic units have to be controlled. When does an arithmetic unit work? Where does it take the input from? Where does it write the output? Where does it send the output to? All those things are there. It's control aspect of computing. We are not discussing that here. There will be in a future course. But in this course, we will see some of the basic circuits which perform arithmetics in computers. When you say computers, you need not imagine a big Pentium P3, P4, anything. A simple calculator is a computer. Even a much simpler circuit, computing circuit. We have seen that so far we have used logic gates in order to implement some of those circuits, like parity generator, for example, code converters. Whatever is the circuit definition, input-output specification, we finally reduce it to a Boolean equation, minimum sum of products or product of sums, implemented using gates. And gates are basically logic devices, logic circuits, wherein you have true or false inputs and true or false outputs. So when a combination of true or false inputs give rise to a specific output being a true or false. How do you translate this logical operation into a mathematical or arithmetic operation? This is what is required in a computer. In computer we give numbers as inputs and we want numbers as outputs. So how do you convert or how do you transform these logical gates into arithmetic circuits? Again, it is simple because of binary nature of the numbers we are representing. Because we talk about binary representation of numbers, however big the number is, we have to translate it into binary format, binary representation, zeros and ones. So as long as you have zeros and ones as inputs of circuits, you can have an output which is also 0 or 1. You can interpret it as logical signals and logical inputs, logical outputs, or interpret it as arithmetic circuits whose values can be 0 and 1 and the output is 0 or 1. So it's a question of interpretation of the same logic gate as an arithmetic circuit rather than a logical circuit. Simple example would be a gate in which I have two inputs as 0 and 1. If I want the sum of this, I want the sum of 0 and 1. So the output can be 1. If both are 0, the output has to be 0. So this is the type of arithmetic operation will perform using the same logic gate. So the simplest of arithmetic operation is a adder. Of course, all of us know that. Let us say we have two numbers A and B, and we want C, which is sum of A and B. This is a sum operator, not the OR operator. Arithmetic sum. Since the numbers are binary, each of them can only take a value of 0 or 1, right? So I have 4 values. If both are 1, what should be the output? The output sum is 2, which cannot be represented with one binary digit, because binary digit can only represent 0 or 1. So I know the number will be 0. Sum is 0. It's truncating, right? I have something like trying to add two numbers, single digit numbers, and I have only a single digit to represent my result. The number exceeds the single digit number, naturally it will only show the first digit. The second digit will be discarded. Suppose I have a single digit representation, binary decimal representation, both inputs and outputs. As long as the number is less than 9, I can get the actual value. If the sum is more than 9, then the first digit only will appear, the second digit will be discarded. Suppose I have two numbers added 5 and 5, answer is 10, but 10 cannot be accommodated to my single digit output. It will only represent the first digit 0 and the second digit 1 will be discarded. So that way when you look at it, the sum is 0, but we need to take care of the fact that sum was 0 because, not because both were 0, because both were 1. So I need to have one more output. So the second output, so I will not even call this C now, I will call it S as a sum. So S is the sum, and I will call this C as the carry. So S stands for sum, C for carry. The carry is when you have a digit which is overflowing, that overflow has to be accommodated elsewhere in the next time, the next computation stage. The next time you compute, you have to take into account this overflow before you can proceed with the addition. So I need a carry which is only 1 in this case, all other cases it is 0. Isn't it? The simple adder. So I have two inputs and two outputs. So this is going to be my adder circuit with two inputs A and B, two outputs S and C, adder, and you can very easily see that sum is exclusive OR of A and B and C is AND of A and B, right? So I can, without having to go through corner map and Boolean algebra, reduction, everything, I can look at the truth table and write sum as A exclusive OR B, C as, is that right? So basically this circuit is nothing but and the carry is nothing but a gate, I don't know, without spoiling this. Isn't it? So an exclusive OR which takes this A and B and gives a sum, and an AND gate which takes this A and B and gives a carry. But now this is a one bit addition. Suppose I have no number is small enough to be represented by one bit. In that case, you don't need a computer, you don't need a calculator, you don't need an electronic circuit. Supposing all you can do with your computer is add 1 and 1, nothing more than that. So you don't need a computer. So I need to naturally represent my numbers by larger number of bits. So my decimal number, the whole range of decimal number I want to operate from 0 to whatever number, infinity, because infinity is only a fictitious quantity, very large number you want to deal with. You want to add, only then you need a computer really, a calculator, you punch these numbers to get the output when the number is large, not when the number is very small. Somebody asks you to get 3 and 4, do you need a calculator for that? You don't. Maybe after some time, right now at least people can add single digit without having to resort to calculator. Earlier it used to be very large numbers, but now we depend on computers and calculators so much. Single digit we still don't need calculators, right? But then we don't need this circuit. So naturally this one bit is only one of the several bits that you will have in your number representation. So this A and B will be really multi-bit representation of the decimal number. We have gone through the digital to binary representation. Is that right? Decimal to binary representation. So when you are given number A and B are both decimal numbers of several digits, the first thing you do is to convert them into binary and then add those numbers. So reasonably assume that A and B are both multi-bit numbers. So that means when I add this A and B, the first digit, so let us say I have multi-bit A and B. A and B are multi-bit numbers. To start with, I will call them 4 bits. Say 4 bits. So now represent A as A0, the lowest significant bit, A1, A2, A3, B as B0, B1, B2, B3, and I will have the sum as S0, S1, S2, S3, right? And then I may have a carry from A3 and B3, so there will be a carry out also in addition to this. So this is sum, A, B, sum and a carry. Carry, CO for carry out, output carry. So when I consider A0 and B0, first two bits of A and B, first bit of A and first bit of B, naturally there is no carry because it is the very first bit from A and very first bit from B, so I can use this hardware. But when I try to do the addition of A1 and B1, I need to consider not only A1 and B1, I need to also consider the carry from A0, B0. So the carry from here has to flow into this, and carry from here has to flow into this, carry from here has to flow into this, and the final carry is what we say here. Isn't that? So this is the carry in and this is the carry out. In addition to, so this carry is a carry out. Output carry which has to be fed as the input carry in the next bit addition. The next stage of the binary arithmetic, I need to take the output carry from the previous stage and feed it as the input carry. So C out would be C in for the next stage. So this adder will not do the job, cannot do the job. This is having limitation, can only take 2 numbers, not the third number. Such an adder is called a half adder. A half adder is one which can only take 2 digits and add the sum and get the carry, but not take into account the carry provision from the previous position of the addition. I need to expand my circuit into a circuit in which I will take my A, B and C in. The C in being the carry from the previous bit position, and get my sum and CO. Seen is the input carry, CO is output carry. Input carry comes from the previous position. If this is the nth bit, this is n minus 1th carry out of the previous bit. So this is the nth bit. So if I call this, generalize it, Ci, Ai and Bi are the ith bit of A and ith bit of B. This is C in nothing but CO Ci minus 1 from the previous position. I get Ci minus 1 and I get some ith bit, carry ith bit. And this Ci will become, in the next stage, carry in, and so forth. Such an adder which can take into account the carry from the previous position is called a full adder. Which is only of practical use. This is not of practical use except for the very first bit position. The very first bit position in a large number, multi-bit number, the very first bit can be added using a half adder, but all other bits have to be added with a full adder. But of course, for uniformity's sake, even the first one you can make it as a full adder and connect the carry to 0. So I don't want to have two types of circuits. Suppose I have 16-bit numbers. I'll have 16 A's and 16 B's. So instead of having 15 full adders and one half adder, I can have 16 full adders for uniformity's sake. The very first full adder, I will make the carry input as 0. Then I will have uniformity. Is that right? So what is the behavior of this full adder? How does it look like? Full adder truth table. So we'll call A and B, C input, sum and C output. Sum is 0, 1, 1, 0. 1, 0, 0, 1, carry is 0, 0, 0, 1, 0, 1, 1, 1. You can look at this and write it very easily. For example, if you take this, there are 2 bits, 1, third bit is a 0, 2 bits 1 lead to 2, number 2, 2 is 1, 0, so sum is 0, carry is 1. All you have to do is to count the number of ones, A, B, C. In ABCI, count the number of ones. If it is a 0, you put a 0. If it is a 1, you put a 1. If it is 2, you put a 0 and the 1 gets next one. If it is a 3, you put a 1 and 1 in the next one. That's all. So the number can be, all the 3 can be zeros, all the 3 can be 1. If all the 3 are 0, this is only a binary representation of the number of ones. Is it not? The output is nothing but the binary representation of the number of ones in the truth table. Only thing this is, if all are 0, so 0, 0. Take this for example, there are 2 ones, output is 1, 0. Binary representation of 2 is 1, 0. This is binary representation 3, binary representation of 3 is 1, 1. So this is how you write the truth table, very easy. Number of ones. If it is 0, you put a 0. If it is a 1, you put a 1. If it is 2, you put a 0, 1. If it is 3, you put a 1, 1. There you go. Very simple. So now I can write the truth table for this. So the truth table is there. I can put the corner map for this and get the simplification and draw the logic for my full adder, which I can going to give it as an exercise. I am going to draw the corner map. Simplification I am going to leave it as an exercise to you. It's very easy. There in all the books. The truth table for binary, table for 1. So I will call this. Oh, I'm sorry, it's only 3. Eight rows, no? A, B, C, I. This is sum. So first row is 0, Ci is 1, 1, 0, 1, 0, 0, 1. This is the truth table and the corner map. This is the K map for S. First row is 0, second row is 1, third row is 1, fourth row is 0, fifth is 1, sixth is 0, seventh is 0, eighth is 1. We know that, how to draw. You can simplify it. Apparently there are no prime implicants, but remember we had this type of pattern in our parity generator. We had this pattern in also in one of those converters, gray code converters. So it's an exclusive OR solution. I leave it as an exercise to you to get this expression. I will give the expression to you. It is A exclusive OR B exclusive OR Ci. Please get this expression as a homework. As a very easy pattern is there. The pattern has been identified earlier in our parity checker, parity generator. And the carry is carry out is zero, 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 one. There are 4 ones. The only way to join them will be three prime implicants, all essential. 3 essential prime implicants. You can add them or them really, not add them. CO would be AB, ACI, BCI, or AB, CI, ARB. This is the carry output. If CI is the carry input, CO is the carry output, A and B are the bits. Can be applied to any bit, AI or BI. It can be third bit or fourth bit or fifth bit. If it is a fifth bit, this is the fifth bit input of A, fifth bit input of B, fourth bit output of C, this will be the fifth bit output of C, right? Ci is the one bit before the current bit. CO is that current bit output for the carry. I can also write it as an, I want to give it as an assignment, I can also write it as CIA exclusive or B. We will use it sometimes, not now. Occasionally we will use this expression for carry and not this expression. That means this should be equivalent. That means this should also be right. I can tell you quickly, intuitively, without having to go through Boolean algebra, how this can be right. When you say AB, you are taking these two terms into account, right? This one and this one have been considered in getting this expression. Is that right? AB is same as this and this. I had this one extra one, this extra one. In order to make my prime implicants smaller, my sum of product expression smaller, what I did was to combine this one with a 1 and combine this one with a 1. Remember, this one has already been considered in this expression. So what I am saying is, again I will do it here one more time. Consider this carefully. I have already considered this as AB. BCI. Wait a minute now. Let me see probably. BCI, AB. AB is what? C0 is 0, okay, 0, 0, 0, 1, BCI, 0, 1, 1, 1. So when you consider this as BCI, AB, we will first take AB. Which is AB? AB, right. Let us say this has already been considered as AB. I have these two ones left. I combine this one with the one to make my product terms less by 1 literal. Whenever I combine two ones, my product term gets reduced by 1 literal, isn't it? Every time I combine a factor of 2, 1 literal goes out. 4, if I combine, 2 literals go out. If I combine 8 terms, 3 literals go out. So that was the reason why I had to make this and this, even though this was not necessary to have combined this with this and this with this, because this has already been taken into account. Now if I consider these two terms separately, what is this? This is A B bar Ci, and this is A bar B Ci. So if I take Ci out, becomes A B bar or A bar B. Is that right? These two terms is this, which is equal to Ci times A B bar A bar B, which is nothing but A exclusive R B. So this is same as Ci A exclusive R B. That is this. So I can either write it this way by grouping the ones more than once. Grouping these two, this one 3 times actually. If I group this one 3 times, I get this. If I do not do it, if I only group this here, which I get AB, and these two ones I separately write as a sum of product term, it reduces to an exclusive R. In other words, my CO can be AB and AB or Ci and ARB or A exclusive RB. I will use this to my advantage whenever, again as I said, hardware advantage. Suppose I am asked to give an exclusive OR solution. I want more exclusive OR gates and less OR gates. For some reason, maybe I have an exclusive OR array and I want to use as many exclusive ORs as possible in my solution. I can use this. Sometimes I may say give me the simplest possible solution, then in that case I have to go for an OR solution. Exclusive OR gate is definitely a more complex gate than an OR gate, simple OR gate. So this is the philosophy of minimum sum of product expression. Minimum sum of product always expression not always gives you the most optimum solution in terms of practicality. We saw it in the case of gray code converter. We saw it in the case of parity generator. We saw it in the case of, if I did not use this exclusive OR solution, I will have 4 min terms, each min term with 3 literals. There will be 4 AND gates with 3 inputs each and 1 OR gate with 4 inputs, and each of these ABC inverted. So 3 inverters. 3 inverters for ABCI, 4 AND gates with 3 inputs each, 1 OR gate with 4 inputs. As against that, I am now having 2 exclusive OR gates with no inverters. A need not be inverted, B need not be inverted, Ci need not be inverted. All I need is 2 exclusive. Suppose I get 2 exclusive OR spare. I am having a big hardware board in which I am doing several things, and I happen to have a couple of these exclusive ORs unutilized. I will use it. So there is after the minimum sum of product expression, all this corner mapping and minimum sum of product expression, try to get as many ones as possible to be grouped together. All that is fine. I am not saying you should not do it, but after that also have a little, be a sort of a little bit vigilant. After that, some little manipulation can lead you to a very simple or elegant circuitry. That is what we did in the case of exclusive OR gate in use of in parity check generator. That is what we did in gray code. That is what you have done here. That is exactly what I am doing here. Sometimes A or B can be replaced by exclusive OR B if necessary. I am not saying do it every time. Supposing an exclusive OR solution is needed for some reason, some practical reason, because you have stocked exclusive OR gates, a large number, and want to use it, rather than go to a market and buy an OR gate. That is a good enough reason. Or I have an exclusive OR gate unused in my board. I use it rather than going and finding another OR gate and finding a place for it and connecting it together and all that type of thing. All I am trying to say is these two expressions are equivalent. Depending on whichever you want, you can use it, but generally the people stop with this in the book. This you can see, but this will use later on. We are going to use this later on in our consideration for simplification of circuitry. We will use it sometime. But meanwhile, I thought it's worthwhile to say this to you. Now what we have done so far is to do a half adder, 2 bits, both A and B, to be added with a carry. 2 input, 2 outputs, a half adder. Not of much practical use except in the least significant bit where there is no carry input. But generally when you are doing a multi-bit addition, 1 bit not having a carry is not significant at all. You can as well forget about the half adder and do a full adder in which there are 3 inputs, A and B, and the previous carry output as the input of the carry, 2 outputs, sum and carry, and sum is coming in exclusive OR format and carry can come in this format and this format. This is for a single bit. As I said, we have to do multi-bit addition. Suppose I have a 4-bit number as I assumed here. A and B are multi-bit additions, both. So how will it look like? The 4-bit adder will look like I have 4 bits. A0, B0, A1, B1, A3, B3. Now the carry from the previous input, let us assume all of them to be full adders for uniformity, for sake of uniformity. This carry in, I will ground it, make it 0, because very first bit there is no carry in. This carry out goes into carry in. This carry out goes into this carry in. This carry out goes into carry in. And this carry out is the, so we will have sum 0, sum bit 1, sum bit 2, sum bit 3, and the final carry bit will be my C3. So my sum will be 2 4 bits added. I can have a sum of how many bits? 5 bits, because last bit can produce a carry. So 2 4 bits, when I add, the sum can be, when I say sum, that includes carry. The total number I get at the output will be 4 or 5, depending on whether there is an output carry or not. So I should allow for 5 bits. Whether I may have it or not depends on the numbers. If both the numbers are zeros, the output is 0, no need for a carry out. But since I don't know the numbers A and B, if I knew the numbers A and B, why should I add? So if I don't have, since I don't know the numbers A and B, it's a possibility that can generate a carry at the output. So the final number will be, so when you add 2 4-bit numbers, the result can have up to 5 bits. So the 5th bit is nothing but the carry out of the 4th stage. This is called, the whole thing is called, so when you are going to the shop to buy a 4-bit adder, you have only these A's and B's to be fed in. A0, B0, A1, B1, A2, B2, A3, B3. Out comes S0, S1, S2, S3 and C3, and you have to give the C in as the input, as 0. This is called a 4-bit full adder. As a one package. Whatever I drawn inside the rectangle is a one package of IC integrated circuit, wherein I can feed 4 A's, 4 A bits, 4 bits of A, 4 bits of B, and the carry from the input. Why do you need the carry from input? Of course, the first stage the carry is 0, but this can be, suppose I want an 8-bit adder. What will I do? For an 8-bit adder, I will use this 4-bit full adder. I will use another 4-bit full adder, and I will give A0 to 3, B0 to 3. This arrow with a cross means there is more than one bit. I write here 0 to 3, that means how many? 4. A0 to 3 means 4 bits of A. B0 to 3 means 4 bits of B. But 4 bits of B. A single arrow cannot show 4 bits. So you put a cross across it. If you know, this means it's more than one input, that's what it means. An arrow cross in a digital drawing indicates there's a more than one bit input. Since if you know the number of inputs, you can write 4. You know more than one, but you are not sure how many, then you put a cross and stop. And similarly, I get here A5, A4 to 7, 4 bits. This is my 4-bit. B4 to 7. So I have now two numbers, A0 to A7, B, B0 to B7. 8-bit numbers. A is an 8-bit number, B is an 8-bit number. The numbers are A0 to A7, B0 to B7. These are the bits. So the sum should be, can be 8 bits or 9 bits. 8th bit can have a carry. So I will feed the output CO, which is actually C3. C3 of the previous block as the input here. So don't assume that every time the first bit will have a 0 input. Don't assume that the first bit of the 4-bit adder will always have a carry input of 0. If it is an intermediate stage in a multi-bit addition, then my input carry would be the output of the previous block. This bit of 4 blocks, block of 4 bits, output feeding into a block of another 4 bits. The output carry C3 goes as input carry Cin, and output of this is C8, C7. So this should be sum 0 to 4, sum 0 to 3, 4 bits, 4 to 7, 4 bits. So this is 4, this is 4. So 4 bits, 4 bits. C7. So C7, S4 to S7, S0, S3 to S0. If you want to write S7 to S4, S3 to S0. First 4 bits, second 4 bits, the last bit is the carry bit, is the 9th bit. Like that you can add, you can cascade in a number of 4 bits. 4 bit is generally available as a slice. 4-bit adder is a component which is available as a ready-made circuit. Sometimes 8-bit adders are available, but not 16-bit adders. You can't buy a 16-bit adder. You can't buy a 32-bit adder. You want to build a 32-bit adder, you have to buy either 4 bits or 8 bits. If 8 bits is available, you buy 8 bits. Otherwise, buy 4-bit adders and cascade them. First 4 bits feeding to the second 4-bit carry of the second 4-bit feeding to the carry in of the third 4-bit, etc. Each of these will give you 4-bit sum, 4-bit sum, 4-bit sum, 4-bit sum, 4-bit sum. The last carry would be also be considered. Intermediate carries will feed into the next stage. and the very first carry in is 0. And for A0, A's and B's are fed into each of these blocks as is shown here. This is a multi-bit adder in 8-bit adder, 8-bit full adder. Later you can go on building any number of 4-bit adders to make a higher bit adder, 32 bits, 64 bits. But let us examine whether it is a very efficient way of doing it. Any questions so far on the half adder, the full adder? How do you combine full adders to 4-bit adders and 4-bit adders into multi-bit adders of any number of bits? The concept of carry in and carry out, sum. So individually each of these blocks will have A exclusive or B exclusive or C as the sum, and AB or C A exclusive or B as the carry circuit. So there are so many gates inside. Take it as an exercise. Find out how many gates will be there in a 16-bit full adder, assuming the first stage is also a full adder. Let us not assume a half adder. Let us assume for uniformity's sake there are 16 bits. I am adding using this scheme. That means I will have 4 of these, 4-bit adder. And in turn a 4-bit adder will be like this: full adder, full adder, full adder, full adder. That means there is going to be 16 full adders, and you know each full adder is having the sum circuit like this and carry circuit like this. So find out and list using this equation and using this equation. For sum use this equation always. For carry you can use both these equations, first this and this. Each case list the number of gates. When you say number of gates, you should, whenever you asked to give the number of gates, you should give what is the type of the gate. You can't say 17 gates. You will have to say 8 gates of 3 input AND gates, 8 gates, 8 3 input AND gates, 6 2 input OR gate, 4 4 input OR gate. Like that you should give a list of type and the number of inputs. Only then it becomes complete. As if you can go to a market with that and a shop with this and then buy those. Make a shopping list of number of gates required to build a 16-bit full adder. Now, having said that, let us quickly see whether it is the most efficient way of doing the job. When I say efficiency, we talk of many things. I already said in the beginning. The speed is one thing, the power consumption, the number of gates so that the size is reduced. So you can make all in one IC, it will be very fine. So I can save the size. For a moment you forget about that size. Assume that it all will run in one IC, one integrated circuit. We will not even make 4-bit, 4-bit, 4-bit. We will try to make, suppose you want a 16-bit gate, we will try to integrate 16 of those units inside one small IC block so that size can be saved. We will not talk about power saving now because I have not told you how to compute the power requirement of a gate. But from the speed, one of the criteria, one of the parameters I have been stressing from the beginning is the speed. How much time does it take to complete a 16-bit addition? Do you have any idea? How much time does it take? Suppose I have A and B. A is 16-bit, B is 16-bit, all of them are available to start with. I am giving you a 16-bit number for A, another 16-bit number for B, and say go. And we are asked to do the addition. Can you do it instantaneously? No. Why? The gates themselves will take time. For example, even with a single bit adder, or let us take this, even this single, very simple full half adder. Moment I gave A and B, the output S and C are not available because these are not, however fast the circuits work, gates work, there is a finite time delay. So there is a time delay involved in the propagation of these values for the switching operation of exclusive OR gate and switching operation of this AND gate before you get the result. Since we don't have an idea of the gate delays of individual exclusive OR gate and individual AND gate, and then it will depend on the number of, the delay will depend on the type of gate and the number of inputs. Both decide the gate delay. The gate delay depends on the number of inputs to the gate as well as the type of the gate. Since we don't know anything of all those things, we will only simply say the time it takes for the output to come after the input is given. We will call it propagation delay. The delay of propagation of the inputs to the output is called propagation delay. There is only one exclusive OR gate and one AND gate. When you go to a full adder, there are two exclusive OR gates and a two-level gate, one AND gate feeding into an OR gate. Whether you use this model, let us use this model, one OR gate, one AND gate feeding into another gate. So there is going to be some delay there. So there is going to be delay in these two stages of gating. Here also there is two stages of gating. A exclusive OR B has to be fed into this C. First exclusive OR gate will find A exclusive OR B. Second exclusive OR gate will take that and put it into C. So two levels. Here is one level of gating, some propagation delay. Here there are two levels of gating, propagation delay. So since full adder we have taken as a unit of delay, unit of our consideration, because half adder is used only for the first stage, we will forget about it for a moment. For all purposes of calculation and standardization, we will assume full adder is a basic building block. A single bit full adder, one bit full adder is a basic building block. We will call the propagation delay of the full adder TP. That consists of two parts, the carry and the sum, whether sum comes first or carry comes first. Because sum has one path, carry is another path. Whichever path activates first will come out first. We will not worry about all that. We will wait. We are only interested in the carry now, because the carry has to come from here. It has to come from here, go here. It has to come into this, go here, go here. Even if the sum comes a slightly more delayed, sum and carry may not have equal propagation delays. We don't know. We will have to look at the gate structure to see which is faster. Sum can be faster, carry can be faster. Let us not talk about it for a moment. For a moment we will only concentrate on carry propagation, because carry propagation is more important. The carry has to go from here to here, here to here, here to here, here to here, and then from here. So for 16-bit full adder, which I asked you to do as an exercise, carry has to propagate through 16 stages. First stage has to go into second stage, second has to go to third, finally it goes to 16th stage. So 16 propagation delays have to be carry delay have to be accounted for. Meanwhile the sum will come, because as soon as A and B are known, sum can only once the carry comes, the carry triggers the sum, this carry triggers the sum. It's something like a domino effect. As soon the carry comes, sum comes, but then carry goes on. Carry goes from here to here, leaving sum behind. Goes from here to here, leaving sum behind. Sum may be a slightly delayed carry, but then before the carry goes to next stage, the sum would have been settled. So if you don't worry about the minor difference between sum carry and the sum delay and the carry delay, let us only worry about carry delay, because that is the most significant, because it has the more significant of the two, because it has to travel a wide, long distance. So the total propagation delay is 16 carry propagation delays. Carry of a full adder is the carry propagation delay. 16 of them has to be used. It's just 16-bit adder. It could be a 32-bit adder, 64-bit adder, you can imagine. So we have to think of, if you want a faster speed, you want to talk about 1 gigahertz Pentium, 2 gigahertz Pentium processor. What is a gigahertz? In terms of clock frequency, nanoseconds. Giga is 10 power 9. Inverse of reciprocal of 10 power 9 is nano. We are talking about nanoseconds. The whole operation, when you say computer works at nanoseconds, the whole thing has been done. some addition process, some multiplication process, some other process. And we are talking about full adder here. And how many such things will be there in a computer? Adding two numbers is the least complicated thing you can think of in a computing. In a computing environment, there are so many other more complex things that have to be done. So that means we have to definitely try to do something to reduce the carry delay. There are several techniques. To exhaust all of them will be beyond the scope of this lecture series, but I thought at least some of these concepts are important. It has to be drilled in the beginning. When you are teaching first course in digital, when you are learning first course in digital, you need to understand certain parameters. See, at least you should know a problem exists. Later on you will have opportunity to learn about solutions of this. So we will take one system, one technique of improving the speed of a carry. One technique of reducing the propagation delay of a 4-bit full adder we will see in the next lecture. But that is not the only way to do it. There are several other methods. We will not be talking about all those methods. We will take one simple method of reducing the propagation delay of a full adder, 4-bit full adder, in the next lecture.